Polyethylene terephthalate, commonly known as PET, is one of the most widely used plastics in the food packaging industry. It is also the most easily recycled plastic in the world. PET is synthesized in a process called esterification. Its monomers, ethylene glycol and terephthalic acid, combine in the process of electrophilic substitution. The ethylene glycol deprotonates the OH group on the terephthalic acid, and water is formed as a leaving group. Then, the two monomers attract to form the polymer, polyethylene terephthalate, or PET. The overall structural arrangement of the polymers leads to its many different applications, from packaging for plastic bottles to fiber synthesis in clothing production. PET in plastic bottles is the same chemical as in your polyester-based clothing. However, the intermolecular structures contribute greatly to the purpose of the material, which is why your workout clothes allow your skin to breathe, but wearing a plastic bottle would not. Three major structural factors include the length of the polymer, the level of crystallinity, and the orientation of the molecules. The length of the polymer contributes to its intrinsic viscosity. For example, a longer polymer would have more entangled arrangements and therefore a higher intrinsic viscosity than a shorter polymer with fewer entanglements. This idea of intrinsic viscosity also contributes to the need for drying PET before use. If water were present in the reaction, it would decrease the polymer lengths and consequently the intrinsic viscosity because of its polarity. The polar parts of PET would react with the polar water molecule to break the polymer chain into shorter segments. Polyester fibers have much lower intrinsic viscosity, closer to 0.6, than bottle-grade PET, which is between 0.7 and 0.8. This makes sense because these fibers are far more malleable than their plastic bottle counterparts. Crystallization is the alignment of polymer chains and is measured using density, because more organized polymers are denser and allow more molecules in the same amount of space. In the case of crystalline PET or CPET, the crystalline structures are not broken down until just prior to extrusion, where the PET is essentially melted. In post-extrusion processing, the PET pellets are heated above the melting temperature and then cooled quickly so the levels of crystallinity can be controlled or minimized. When the plastic is cooled very quickly, it is not able to form the thermodynamically favorable crystalline structures, and entanglements get in the way. When crystallinity is increased, often by a not well understood process called nucleation, PET becomes white and brittle. Its density increases, and the highly arranged structure obstructs light. The amorphous cousin APET, however, is more impact resistant and clear, indicating a direct relationship between the level of crystallinity and the transparency of the plastic. In other words, less crystalline structures are more transparent. Light is able to travel freely through the randomly arranged polymers. In addition, the change in crystallinity affects the boiling point of the material. A highly crystalline structure has many more intermolecular forces to overcome, explaining its higher boiling point. It needs more thermal energy to break the attractions. A more amorphous structure, on the other hand, has fewer intermolecular forces because of its more random arrangement. Thus, it requires less energy for its structure to be overcome. In practical application, this is why some plastics can withstand oven temperatures, like cupcake pans, and others cannot, like your prom dress. Even after the synthesis of these crystalline structures, the physical characteristics of PET can change. For example, in thermal-induced crystallization, the resulting crystals in the molecular structure significantly increase the plastic's thermal properties. CPET has a much higher heat deflection than its APET counterpart, which becomes distorted at these extreme temperatures. So why do these crystals form in the first place? This is due to the stiffness of the PET chain. The presence of a bulky benzene ring adds the structure to the polymer, allowing it to form lamellae and crystallize. Finally, orientation plays a large role in the structure-function relationship of PET plastics. The orientation of a polyester fiber for fabric or textiles is generally in one direction and is largely in long axial strips. Bottle-grade plastic, on the contrary, is biaxial, meaning that it has two directions of orientation. Consequently, it also displays a much stronger tensile strength in both the axial and hoop direction and is more resistant to changes in position, where axial and hoop directions refer to tests on PET cups that are cut up and down and circularly, respectively. These mechanical improvements to PET indicate that orientation plays a major role in the physical strength of plastics. So, the next time you get a plastic cup, maybe you can impress your friends with a little PET knowledge. Thanks for watching and have a great day.